Astronomers learn a great deal about the universe by observing the types of light emitted by astronomical objects. While our eyes can only see light that falls in the visible part of the spectrum, it also includes radio waves, microwaves, infrared light, ultraviolet light, X-rays, and gamma rays. The only real difference between these types of light is the amount of energy they have. All objects emit varying types of light or electromagnetic radiation depending on the object's temperature. Light can behave as both a massless particle called a photon and a wave. Waves diffract. When they pass through small openings, they spread out after they pass through. Two waves can also interfere with one another. If the waves are in sync, they add together to become stronger, and if they're out of sync, they cancel each other out. This classic double slit experiment demonstrates how light acts as a wave. In my hand, I have 3 pencil leads that are separated to create 2 tiny openings. When I shine the green laser through those openings, the waves interfere with one another and create a pattern of dots on the paper. If light behaved only as a particle, we would just get 2 dots on the paper. We can also show how light acts as a photon, or a particle. This ball is painted with fluorescent paint. When a photon of sufficient energy excites the electrons in the fluorescent paint, it activates the pigment. The red laser is low energy, and it's not strong enough to activate the fluorescent paint. But the green laser has higher energy, and it activates the fluorescent pigments to reflect orange rather than green. Nothing can go faster than the speed of light. It travels at nearly 300 million meters per second, 186,000 miles per second. This becomes a very handy measuring stick for astronomers because distances in space are so large. Astronomers often use the distance light can travel in 1 year, called a light year, as a unit of measure. Astronomers use the information hidden in the light produced by stars to learn more about them. This is called spectroscopy. We can take white light and use a prism to split it into the different colors of a rainbow. Astronomers can also do this with the light coming from stars. The light coming from a star like our sun looks like this. The dark bands happen because the light from the star passes through the star's atmosphere before reaching us. And the elements in the star's atmosphere absorb the light at certain wavelengths. Each element absorbs at different wavelengths, so it creates a pattern similar to a fingerprint. This is the pattern created by hydrogen. You can see that our star contains hydrogen because the lines match up. Helium is also in the star because the pattern matches. The star doesn't contain any water, however, because the oxygen line doesn't match up. Sir William Herschel discovered the existence of the electromagnetic spectrum beyond visible light by accident in 1800. He set up an experiment like this one, using a prism to break sunlight into the different colors and putting a thermometer in each band of color. He was surprised when he found that the highest temperature was in the thermometer just outside the red band of color. He had discovered infrared light. Soon after, scientists began discovering other types of electromagnetic radiation, although it took more than a century before all the different types of electromagnetic radiation were understood. In the late 1800s, director of the Harvard College Observatory, Edward Charles Pickering, was producing images of stars etched on glass. His computers, a group of women who ultimately established the foundations of modern astrophysics, measured the brightness, positions, and spectra of the stars, like the one we looked at earlier. One of the women working in the lab, astronomer Annie Jump Cannon, analyzed hundreds of thousands of stars and is credited with creating the modern stellar classification system based on the patterns of stellar spectra. It was later realized that the group she created corresponded to temperatures of the stars. O stars are very hot and blue, while M stars are cool and red. Astronomers now have the technology to observe astronomical objects in all ranges of the electromagnetic spectrum. Most electromagnetic radiation from space can't reach the Earth's surface, so detectors have to be sent up above the Earth's atmosphere, placed on mountaintops, attached to a giant balloon that hovers above the atmosphere or sent into orbit on rockets and satellites. The images these detectors produce use visible color to represent wavelengths of light that are invisible to our eyes. Imaging astronomical objects across all the wavelengths of the electromagnetic spectrum can tell astronomers a lot. The mass, size, chemical makeup, distance, speed, magnetic fields, and temperature can all be observed. Spectroscopy has provided astronomers with invaluable information about the cosmos and is still shining new light.